Let's then begin our discussion of nuclear and particle physics with the discovery of the nucleus, without which there can be no nuclear physics. So at this point, the beginning of the 20th century, the electron had been discovered. Atomic theory was now pretty well established. It certainly was used in chemistry with the periodic table, working with all its bins as separate things. And also, to understand thermodynamic properties, one could just understand the movements of the atoms and molecules. And the other properties of the materials could also be explained with atomic theory. However, atoms had parts. They could also change. We knew that due to radioactivity having been discovered, and also the electron being discovered by J.J. Thomson. And so one needed a model for how this thing that could change and have parts, how those parts went together. J.J. Thomson proposed the plum pudding model, in which you have a kind of a uniform pudding of positive charges in which the electrons that he had discovered were the plums, and so you have the various plums inside the plum pudding, or more likely, you have this uniform positive charge medium in which the electrons move around, giving you totally a neutral charge as a total. So how can you test this structure? Well, in physics, what we often do is we shoot particles at a target and see how they scatter off. That's a tried and true method of doing physics. Should point out that one can both use this to test the structure of things, but also the way things interact. In this case, for the nucleus, the idea was to test the structure. So Rutherford, along with Marsden and Geiger, his students, started looking in 1911, around 1911, at how matter might interact. And so they used alpha particles from radioactivity, which are pretty heavy and charged as the projectiles. They made a beam. They put an alpha emitter inside a lead case, left a little hole so the alpha particles would come out as projectiles, and they directed that beam on a piece of gold foil. Gold is ductile, so you can beat it very thin, and so there's only a few atoms thin, so that you're testing the atom. And so the apparatus schematically looks like this. You have the source of alpha particles here in its lead. It comes out, you have the thin gold foil, and you look for what comes out on a little scintillating plate that you view with a microscope. You need to be able to move the microscope around to see how much comes off at what angle. A lot of pictures that you see of this apparatus neglect the fact that you have to have an evacuated chamber in which to do this, because the alpha particles will hit the air otherwise. Here's a picture cutaway of an actual apparatus. So here, this is the source, the lead foil or the gold foil, and the telescope to view. And this is a schematic version of that. So what Rutherford, Marsden, and Geiger found was that some of the alpha particles came back at very large angles, more than 90 degrees, and Rutherford's famous quote was, "It was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." So the fact that you could have these large bounces, these large deflections, indicated there was a small, dense nucleus inside the atom. So rather than Thomson's model, where the alpha particles would have just gone through and knocked out the electrons, instead the alpha particles go through, they bounce off this dense piece